Alright, welcome to one more video here about improper integrals. The first video kind of explained how improper integrals work when you have an infinite limit of integration, and that's not okay. The other type of improper integral is if instead of an infinite limit of integration, you have a limit of integration where the function itself doesn't exist. So if I have f of x, and f of x is only continuous on an open interval starting at a and closed at b, that means f of a doesn't exist. So what we do is say, all right, if I can't really get to a, maybe I can get to some c value close to a. In this case, I'd be approaching it from the right because from A to B goes starting at A to the right of A all the way up to B. Whereas if my open-ended part of the continuity is the upper limit, that's coming at B from the left because from A to B I'm going from A to B. A is to the left of B. One other option is, what if it's continuous from A to C and C to B, but your integral has C inside of it? Well, then you have to split it up at C and then rewrite limits to go with it. Now, this is one that really makes a lot more sense once you see me do it, so let's come down here and actually do this. In other words, if a point of discontinuity exists at a limit of integration, set up a sided limit to evaluate. If it exists in between the limits, set up a separated interval. So let me kind of show you how that works here. So we have the limit from 0 to 3 of the cube root of x minus 1 squared on the bottom, dx on top. So let's see, where is a discontinuity? Well, in this case, a discontinuity exists at x equals 1. So that means we need to rewrite this integral as the integral from 0 to 1 plus the integral from 1 to 3. Okay, that's not so bad. So if I say 0 to 1 and 1 to 3, I would say, all right, I have the integral from 0 to c, and I'm taking the limit as c approaches 1 from the left, because 0 is to the left of 1, of dx over x minus 1 to the 2/3, plus the limit as c approaches 1 from the right, from c to 3 of dx over x minus 1 to the 2/3. Okay, so discontinuous at 1, separated into 2, let c approach 1 from the left and from the right. Now I just need to take my antiderivative and evaluate. So this is really the limit as c approaches 1. Sorry, my pen is being very strange here. Let me try this again. So c is really the limit, that's better, as c approaches 1 from the left. What is happening here? Integral from 0 to c of x minus 1 to the negative 2/3 dx, plus the limit as c approaches 1 from the right, c to 3 of x minus 1 to the 2/3, negative 2/3 dx. Antiderivative. Well, we did that trick a while back. When I was talking about u subs, I kind of mentioned there's like a linear expression raised to a power kind of trick, where basically it's the backwards power rule as long as you divide by the derivative of the inside. So this is going to become x minus 1. I'm going to add 1 to the power. I'm going to divide by the new power and evaluate it from 0 to c. And I'm taking the limit as c approaches 1 from the left. Then I'm taking the limit as c approaches 1 from the right of x minus 1 to the 1/3 times 3 from c to 3. So over here, if I plug in 1, this is going to be 3 times 1 minus 1. I'm sorry, c minus 1. Sorry, plugging in c. c minus 1 to the 1/3 minus 3. Sorry, the left-hand side of the screen, my pen is not wanting to work. 3 times c minus 1 to the 1/3. Really? Sorry, guys. One more time. 1/3 minus 3 times 0 minus 1 to the 1/3, and take the limit as c approaches 1. Well, as c approaches 1, this is really going to be 3 times 0 to the 1/3, and this is going to be 3 times negative 1 to the 1/3. So that goes to 0. This goes to minus 3 times negative 1, which is just 3. So that first limit goes to 3. Now let's try the next one. The limit as c approaches 1 of 3 times 3 minus 1 to the 1/3 minus 3 times c minus 1 to the 1/3. And as c approaches 1, this is going to be 3 times 2 to the 1/3 minus 3 times 0 to the 1/3, because c equals 1, which is going to be 3 times 2 to the 1/3. So from there, I'm just going to realize, well, I was supposed to be adding those two limits together, which gives me a final answer of 3 plus 3 times the cube root of 2. And there's your limit. All right, I'm going to pause this and try and take care of my pen. Be right back. All right, I'm hoping I fixed it. We'll find out in a second. All right, next example here. We have the integral from 1 to 2 of dx over x minus 2. So I'm going to look at this and say, all right, at 2, this does not exist, which means this isn't really allowed to be here. So in order to get rid of it, we're going to rewrite this as the limit as, let's see, we'll call it b approaches 2 from the left, from 1 to b, of dx over x minus 2. All right, I'm going to take the antiderivative, which is going to become ln x minus 2 from 1 to b. And I'm taking the limit as b approaches 2 from the left, which is going to be the limit as b approaches 2 from the left. Didn't need that extra dash there. Of ln b minus 2. Okay, that's supposed to be absolute value, and it actually matters here. Come on, pen. No, it's just being funny. ln, no, don't do that. b minus 2 minus ln 1 minus 2. All right, now here's where it counts. So I have ln b minus 2, and b is headed toward 2 from the left. So this is going to be like ln 0, which is infinite. 2 from the left here doesn't matter because I don't have a b. ln 1 minus 2 is like ln 1, which is 0, and an infinity minus 0 is infinity. So this limit diverges because when we evaluated it, we got infinity. Strange but true. And technically here, this should have been negative infinity. I forgot to put my negative sign in there. ln of 0-ish is negative infinity. So I forgot my negative sign. I apologize. All right. Last one. 0 to 1, x ln x. All right, this one is another one that should probably have some sort of scary skull and crossbones again, because we do a lot of weird stuff in this one. So just stick with me, you'll be okay. I promise you on the AP, it's not usually this many things at once, but I figure, hey, it's the notes, you're just watching me do it, so why not give it a shot? So if we look at this one, 0 is part of our limit of integration. We're not allowed to take the ln of 0, so really what we're doing here is we're taking the limit as a approaches 0 from the right, from a to 1. And again, it's 0 from the right because 0 to 1, 1 is to the right of 0. X ln x dx. So right here, we are going to say, all right, antiderivative of x ln x. I don't know, but it's a product I can't get rid of, so let's try integration by parts. So LIATE, ln x is going to be u. That leaves x dx to be dv. And hold on, my dog needs to go outside. Pause. Sorry, Libby Leibniz dog needed to go outside and go potty. All right, so u is ln x, dv is x dx, so now I need to find du. Derivative of ln x is 1 over x dx. And find v. Nope, that's not what I wanted you to do. Find v. Nope, stop that. What is going on here? Try this one more time. Find v. Nope, still doesn't work. V, haha! Antiderivative of x is 1 half x squared. So then I'm going to say the integral of x ln x dx equals u times v minus the integral of v du, which is really going to become 1 half x squared ln x minus 1 half the integral of x dx. Take another antiderivative, 1 half x squared ln x minus 1/4 x squared plus c. So for ours, we were really taking the limit as a approaches 0 from the right, from a to 1 of x ln x dx, which means I really need to evaluate all of this stuff from, let's see, a to 1, and this is the limit as a approaches 0. Now let's plug everything in. Limit as a approaches 0 from the right of 1 half times 1 times ln 1 minus 1/4 times 1 minus 1 half a squared ln a minus 1/4 a squared. All right, so this 1 half 1 ln 1, that goes to 0. Yay, I can evaluate that piece. Minus 1/4. Now, if a is going towards 0, this is going to be 1 half times 0 times ln 0 minus 1/4 times 0. Aw, nuts. I've got 0 times ln 0, which is like 0 times negative infinity. So we need to do L'Hopital. So if I come over here and off to the side and say, all right, I'm taking the limit as a approaches 0 of a squared ln a. If I go to 0, this is again 0 times negative infinity. So I'm going to write it as a fraction. Ln a divided by 1 over a squared. And now my pen's being funny on the right-hand side. Ln a over 1 over a squared. If I plug in 0 now, this is infinity over infinity. So I'm going to take the derivative of the top and the bottom. 1 over a, negative 2 over a cubed. Simplify, that makes the limit as a approaches 0 of a squared over negative 2, if I'm not mistaken, right? Right, yes, a squared over negative 2, and as a approaches 0, this is going to go to 0, which is going to now come back here. So this thing goes to 0. That already went to 0. And holy cow, finally, the only thing that's left, why is there a giant X there? I have no idea. Things happen on my computer today, but I don't have time to rewrite it. Negative 1/4. All right, so with the exception of the dog barking, my pen not working, me accidentally crossing things out that I never touched with the pen, we finally have an answer. Oh, long story short though, if you have a limit of integration that does not exist for your integrand, you have to write it as a limit. Once you write it as a limit, then you evaluate the integral, plug in the bounds, and see what happens. Just beware that L'Hopital can crop up, as can any type of integration that you've seen before. Partial fractions, integration by parts, U-subs, all that stuff can still happen, so just be on the lookout. Sorry for all the nonsense in this video. I will see you guys in class.